today is Joey Wilson, and he did his research on low-cost blood glucose monitoring system with printed on-demand test strips for implementation in Resource 4 settings.
Thank you, Riley. As you said, my name is Joey Wilson, and this summer I did research under Dr. Delphine in the Department of Bioengineering at Clemson University, and I did my research on diabetes. So first of all, we're going to talk about diabetes. Diabetes, if you don't know, has two types, type 1 and type 2. The most common type of diabetes in developing countries is type 1, which is genetic. It causes people to be able not to produce insulin, so it requires people to inject insulin or eat food to increase their blood sugar. The number of cases in developing countries is expected to double in the next 20 years, and over 70% of cases occur in these countries. People obviously first must be diagnosed to treat their diabetes, but they also must monitor their blood glucose daily to treat their diabetes. Unmonitored cases can cause many complications and even death, but could be easily prevented. And developing countries have the problem that supplies are donated, and that with this, meters and strips must match up, and when they don't match up, it renders the technology useless. So that's a problem. We had 3 goals for our project. We wanted to first develop a method to print test strips on demand using regular paper and a regular inkjet printer with modified cartridges. And the cartridges are modified by taking the ink out and putting in enzymes that may be printed. We also wanted to develop a user-friendly colorimetric meter. A colorimetric meter is a meter that measures an absorbance, which is different from meters that would measure something like oxygen levels output by the chemical reactions. We also wanted to develop a process that is cost-effective and relatively accurate in the range of 0 to 450 milligrams a deciliter of glucose. We used 2 printers in our project, but basically any inkjet printer could be used. That is relatively cheap, and these printers could control the amount of ink or enzyme to the picoliter. The Epson Workforce 30 was newer, but that made the cartridges harder to modify because the cartridges for each color were separate, colors being cyan, magenta, and yellow. It contained a chip to monitor ink levels that made it so that you couldn't replace ink and would have to buy another cartridge, so we had to get around that. The older HP Desktop 50 printer could be easily modified because the cartridges for color were just single. It had 3 slots for each different color. So you just had to take the sponges out and insert the enzyme after you clean the cartridges. It had no chip to monitor ink or that needed to be reset. First, we had to run assays, which are just tests to test the concentration and composition of materials, which this is run in a 96 well plate. Our enzymes were made following Sigma's procedure to make these enzymes being glucose oxidase, horseradish peroxidase, and O-dianosidine, which is a dye. Each enzyme, the buffer dye and glucose, were pipetted in triplicate into a standard 96 well plate, and this is to try to get consistent results. We had to run many different assays. Normally you'd only have to run 1, however, in this case we had to run many more because our enzymes we received from the company were unstable, so we had to make our own enzymes. And our best assay was assay number 9. This is the chemical reaction for our process. Glucose, water, and oxygen react with glucose oxidase to form gluconic acid and hydrogen peroxide. In turn, the hydrogen peroxide reacts with O-dianosidine in a reduced form, which is a clear color. This reacts with peroxidase to turn O-dianosidine into a brownish orange color, which is determined based upon how much glucose is in your blood or whatever you're testing. After sitting for about 30 minutes, we put this into a spectrophotometer to read the absorbances, or respective absorbances. Our project was based off of Byrd's law, which compares absorbance to concentration. If you test many known concentrations and view their absorbances, you can find an absorbance that you do know and basically assume a concentration, which would be the line of best fit, as you can see here. Our squared value was 0.9579, which means this data was very good and could be inputted into our device to be used to test people. This was run at 500 nanometers. We then printed our test strips. As you can see, the design of our test strips is as follows. 45 millimeters wide with a 10 millimeter deep well that is about 5 millimeters wide. We use wax paper, which is hydrophobic, and filter paper, which is very absorbent. And by capillary action, the blood would flow to where the enzymes were printed in blocks. Enzymes had to be printed in layers individually because we didn't want them to mix before the blood touched it. And each enzyme was controlled by the color of the template. For example, we had each enzyme in different cartridges, cyan, yellow, and magenta. So to print, say, glucose oxidase, which would be in the magenta cartridge, on Microsoft Word, you would select 255 for cyan, 0 for yellow, and 255 for magenta, making that color. To see if this template worked, we would apply 8 microliters of glucose and observe the color change reactions taking place. After waiting a few minutes and making sure these took place, we could test our glucometer, which was made from LEDs, photodiodes, log amplification chips, and an Arduino microprocessor. Basically how this works is that these green LED, well, first you have your test strips, and you have 2 test strips that you're using in this process. You have a test strip that has everything on it, including the blood, but not the last enzyme, so the reactions don't complete and the color change doesn't take place. This acts as a baseline. You also have something with everything on it where the color is changed, and in this, you can test to see the difference and thus the relative absorbance. The green LEDs shine onto strips, and the photodiodes take a difference in the light intensities. The log amplification chip gets the signal and converts or sends it, amplifies the signal and sends it to an Arduino microprocessor, which uses our equation to change this absorbance into a concentration, thus outputting your relative blood glucose range. So our results. We got a calibration curve with an R-square value of 0.9571, which is very good. And this means that our glucometer is accurate in a range of about 0 to 425 milligrams a deciliter glucose. Before, I didn't mention why milligrams a deciliter are used as a unit. This is because your target number is 100. If you used another unit, such as maybe grams per liter, the number would be something like 4, and you'd have many different intervals between. Our test strips were made by layering filter paper and contact paper and cutting away the template to leave this hydrophobic channel exposed, as I showed before. Our strips have been printed, the templates have been designed in a rectangular shape, our diode will output the voltage difference, and this will be converted into a concentration. We have an average error of 6 milligrams a deciliter, but a standard deviation of over 40 milligrams a deciliter, but that's okay, I will show. Our color change reactions have been taking far too long to complete, about 30 minutes. You really need data in seconds, and that's what monimeters do. In addition, monimeters are accurate up to about 600 milligrams a deciliter, but because ours is accurate, or ours being accurate up to only about 425 is okay, because if you're that high, you take the same action as if you were at 600 milligrams a deciliter. Our method is very inexpensive, and we use parts that are widely available. It costs about $15 to make our glucometer and cents a piece for test strips, which actually cost about $1.50 to $2 each if you're buying company-made test strips. Our device may be built in countries themselves, which could help the relative economies of each country. And our devices we use as a bridge for those who are waiting to get actual testing supplies, well, professional testing supplies. Although our system is currently not as accurate, it can inform you of a relative range, low, good, or high, and you can take appropriate action. Future work will focus on optimizing our design, optimizing how long, or making our reactions happen faster, and an experiment to assess the shelf life of these test strips. The hope is that the system can be implemented very soon in these countries and help decrease the incidence of diabetes-related complications in these settings. I would like to acknowledge Dr. Delphine, Dean of the Bioengineering Department at Clemson University, for serving as my mentor, as well as Kayla, Gainey, and Kelsey, Byrd for being my partners on this project. I would also like to thank the South Carolina Governor's School for Science and Math, as well as my research advisor, Dr. Clyde Smith, and I'd also like to thank Randy LaCrosse. Thank you very much. Any questions? Surya.
For the printer, you were saying that like first it had ink in it and then you had to replace it. Did you replace it with enzymes mixing ink, or how did that work?
No, we had a process for cleaning the cartridges. Basically, we opened them and we put them in a solution to clean them. Then we shook them in it's actually called sonicating, where you send pulses through to clean, and we did that a few times. So that made them clean, and you could insert enzymes then to be printed. Chris.
How would so would these printers be shipped to these developed countries, or undeveloped countries, or?
Our idea is that hospitals or clinics over there would already have an inkjet printer, and people could just go there to a clinic and receive testing supplies daily, because it's very easy to do. It's also feasible that someone could print these at home, but they need to mix their own enzymes, which could be sort of complicated, but still very cheap.
Can it keep memory or log of daily sugars for several days at a time, or how does that go?
Well, each test strip can only be used once, so depending on the shelf life of these test strips, you can take it back to your home and keep a good amount of them for maybe 4 or 5 days to a week, because the shelf life of our enzyme that has the least shelf life is about 5 days to a week. So we're hoping they could set that one and still be usable. Dr. Brockman.
What technology do commercial instruments use that are so much faster than this reaction?
What we're waiting on to happen is not the reaction itself, but for them to change colors. The color change is what's taking a while for us. The reaction actually happens very fast, and depending on how much oxygen comes off of the reaction, they can tell how much glucose is in your blood sugar. But because of that, the test strips themselves are much more complicated and much more expensive because they have electronics built in. Bailey.
Do you have any ideas of how to make the color change faster?
I guess we could use a catalyst for the reaction, but we haven't found one to use yet. Otherwise, I guess we could try different enzymes, but probably just using catalysts. Dr. Brockman.
Wouldn't the color of the hemoglobin strongly interfere with the color of the enzyme change?
No. You can tell how much it changes using the specific dye we used. Even though it's an orange color, it still changes. And the reason we used green LEDs was so the LEDs themselves wouldn't interfere, because the wavelength is far enough away to not mess with the red. Any other questions?
I'm trying to figure out how to phrase it. Obviously, this would have an economic impact if you could develop something that was cheaper. And I'm wondering, you did this at a university, I was wondering how protected your work would be, like patent, as to the pharmaceutical company that maybe didn't want you to develop something cheaper because that would undercut their profit. How protected is your research?
We've actually filed for a patent, and we're not sure exactly what we're patenting. We're patenting we're patenting our device, but we also need to patent the process as well, because there's specifics of the process that I didn't discuss because of the patent.
Right.
So we're filing for a patent. I mean, I'm going to be part of the patent, so if the drug companies want to pay me like $100 million,
you can be bought.
Exactly. But no, I'd really love for this to be employed, and we have people actually in Tanzania. We've been doing research also in Tanzania and finding the problems to solve. So we're actually taking this technology and starting to employ it at clinics in Tanzania. So if that works out well, we can expand it. But someone at the Biomedical Engineering Conference asked me why we don't employ this in the United States. And it's because it doesn't meet FDA standards. But it's good enough for people. But the standards of the FDA are pretty stringent. So we have to be able to employ it in the United States, we have to expand. And drug companies really don't care about the people in developing countries. They just want to make their money. So it's true. Any other questions?
So you haven't had any visits from angry pharmaceutical CEOs? Do you need a bodyguard? And finally, should I be looking for a new roommate?
No, and
Above your range, does it say it's too high? When the current ones, usually the blood sugar is very high, it says too high.
Yes, ours actually outputs a number, which we're going to explain to people what the range is. The target number, as I said before, is 100, which is an easy number to see and know. We've been taught all our life 100 is good. You want to get 100 in school, so you want to get 100 on your blood glucose test. If it's higher, you need to take insulin. If it's lower, you need to eat food. So we're hoping people could do that.
All right, if there's no further questions, let's give Joey a big round.
Bye.